Thanks, Chris, and good morning, everyone. So I'm going to talk about the operation side of things, and there are two things that Mohammed spoke about that will be themes in my discussion as well. One is time is money, so Mohammed ended with that comment. And the other, you'll see that the analytics that Mohammed was speaking of is similarly applied in our situation as well. So there's a lot of commonality between testing and operations when it comes to the applications of analytics itself. So by introduction, Roger Brooks, Chief Scientist at Guavus, which basically means I'm responsible for the analytics offerings within the company. We are focused on communication service providers and the IoT space. And they all have operational issues associated with them, and of course, the presence of IoT traffic over CSPs is critical in that endeavor as well. We are all chasing the issue of NPS with our customers and customers' experiences. And ultimately, our analytics is about improving that NPS of those specific subscribers, and as a result, the overall experience that they're manifesting. So the first question you have to ask is, what are the important things to improve in increasing that NPS? And when you look at survey after survey in the MSO space, what you find is these three critical factors. Obviously, cost or pricing is important, but it turns out that there are two other factors that are even more important. Their perceived notion of service speed. Even as a subscriber myself, I complain about that all the time. The Wi-Fi reliability within the home, they may not realize that it's not the cable operator's responsibility, but nevertheless, it's perceived that way. And those three factors, speed, Wi-Fi, and pricing, are the principal factors by which they'll determine whether they will make a recommendation to someone else to switch over to their provider. When you look at what they want to see improved, pricing, obviously, everyone wants zero cost, but also service speed. So we see this theme of service speed appearing both in terms of NPS as well as their own satisfaction. And so the question becomes then, how can you make sure that they're getting the best possible service speed itself? And so what we look at is how we can apply analytics to that scenario. So if someone is going to complain about service speed, the way you will notice that most immediately is the fact that they're calling in to the care center. So the care center then becomes some sort of proxy for the technical issues that are inside the network that are affecting things like service speed and so on. So can you use this proxy to actually get a handle on these technical factors that are affecting the customer experience, and as a result, the NPS itself? So let's take a look at the bottom left-hand corner, that mock chart there, and look at subscriber care events that are coming in on the vertical axis, and then as they come in over time of day and so forth, on the horizontal axis. And suppose there's some outage-related event, fiber cut or something of that nature that has happened. And what you would expect then is that event, people will wake up in the morning and they'll start noticing it, and increasingly, more and more people will call in over the course of the day. So the curve, you can see my mouse, no you can't. The curve starts to go from zero and keeps going up and up and up and up. So the problem occurs, people start calling in. Eventually, someone who is monitoring, and human who's monitoring and looking at this is say, oh, there's an issue going on. And so there'll be a recognition of the existence of this problem. And then it will take some time to investigate, and then the actual nature of the problem would be identified. And then again, some time to further diagnose, and then ultimately get to a resolution or a fix, and the problem is fixed. During that entire period of time, people are calling in. Every single call has the propensity to decrease NPS. So NPS is being continuously negatively affected by all this. Obvious statements I'm making, everyone is familiar with this, but just setting the context. The goal of analytics here is to take that problem awareness point all the way down to as close to zero as you can possibly get it, to the point where the actual physical event actually occurred. The human then would be involved in first taking that alert then figuring out what is the actual nature of the problem, and then the solution. And so we have analytics in production today across the MSO space. Some of you probably have our technologies, which are doing just that. The next step, which we're doing POCs and so forth, is going into the blue region and into the red region, which is to actually say that this is the nature of the problem, and then ultimately automate the actual face of the problem itself. So the whole thing then gets collapsed close to zero as possible. The number of care events that are coming in gets shrunk. The impact in NPS goes down, and the overall customer experience goes up. The other aspect of this, which is how we get the budget for paying for these things, is not the intangible aspect of NPS, but the reduced cost of actually diagnosing and fixing the problem itself is what pays for the analytics. So the ROI is measured against that reduced cost. So upper left-hand corner of the screen, there are two ways in which you can do this. One is sort of reactive. The problem occurs, run around and try to fix it. And the other is proactive. Right now, most of the solutions in deployed are about the reactive end of things. The facility to do proactive is there. They're beginning to roll out. So reactive. Across the number of customers that we've deployed our solutions at, what we see is it results in about a 4 to 7% savings in care calls, so 4 to 7% less calls coming in. Truck rolls, another 4 to 7% savings. Now they're sort of a function of each other, so that's why it's similar numbers. And then trouble tickets, 5 to 8%. Now when you think about truck rolls, $60, $80 per truck, the number of trucks you're rolling out, this 5% savings is a lot of money. What we typically find in our customers is tens of millions of dollars per year in savings just from that 4 to 7% as a result of applying the analytics to shrink that yellow region as close as possible to zero. So that's reactive. The thing has actually occurred, the problem has actually occurred, people are calling in and you're just reacting it. What you do there is you actually look at the call rates that are coming in the care center, and you're monitoring that, just like the curve is saying. You're looking at the number that are coming in. And typically on a normal day, you'll see some number, I don't know, let's say 10 per minute or something of that nature coming in. And that sets a baseline. But then all of a sudden, one bright Monday morning, there's a big jump to 30, 40, 50. The analytics has to detect that big jump and not just say, okay, there's a big jump, there's a big difference, let me ring an alert, but actually model it and to say, what is the likelihood that that jump would have occurred? And if that likelihood is very small, technically we call it p-value, then it says, hey, I should alert. So this reduces the chances of false positives. And so that's what the analytics does in its reactive mode in its simplest form. What you also want to do is characterize what is common about all of these things. What you want to understand is how do these different people who are calling in and reporting, how are they similar? How do they cluster themselves together? To use the example of what Mohammed was speaking about with support vector machines and so forth. And that clustering gives you a sense as to what's common across them. What you would find out is that, they belong to this node, and have this version of the firmware on this particular device. And that immediately pings you and says, okay, that's what I got to go and look at and investigate. What that does is it reduces the blue region of the curve. And so as a result, you start to shrink this whole thing and make it much smaller, get to the solution much faster, reduce the number of care events, and as a result, also increase or reduce the negative impact on NPS. One of our operators, we can only discuss public numbers. One of our operators has reported that they see a 1% improvement in NPS. Now, you say 1%, that doesn't seem like a big number. But keep in mind, NPS is a difference of two numbers, right? And also keep in mind, unfortunately, in our industry, MSO space, NPS is around negative 6%. Negative 6%. Zero is, break even, right? There's some industries at positive 50%. Going from negative 6 with a 1% improvement, from negative 6 to negative 5 is a big deal. Just by doing this sort of thing, they're seeing that, and they're reporting that. So that's the impact that these sorts of solutions can have on NPS. The way it pays for itself is in that the operations center is saving 4 to 7% of their budget annually. And the positive effect is on the NPS, a 1% improvement. Before I go into some of the use cases that apply to the proactive side, let me just sort of lay the landscape, if you wish, in familiar terms for what we're ultimately trying to do here. So on the top chart, we have the typical workflow for operations management, where there is some sort of failure happening with a device, and then you have to get to a fix, and then ultimately ensuring that the system continues to be available until the next incident occurs, and so on and so forth. And traditionally, this has been a very intensive, human-led workflow. What we are slowly doing is replacing much of this with analytics. The first examples are in, per the previous slide, and some of the proactive things we're going to talk about, are in looking at the actual data that is coming off the devices and predicting that some sort of service impacting incident is going to go out. There's going to be a video outage in a certain region of the network. And just that prediction itself results in the kinds of numbers we talked about earlier. The 4 to 7% savings, the NPS going up 1%, and so forth. Those solutions are already deployed. What we're doing now is proof of concepts and so forth, moving into the diagnostic end of things and the repair end of things, ultimately getting to the holy grail that everyone seems to want of closed-loop automation of the operations of the network itself. And that requires true artificial intelligence as opposed to machine learning, which is the first page. The way this thing is going to fail tomorrow is not the same as the way it failed yesterday. So you don't have a pattern to go against. Machine learning likes patterns. It can only recognize patterns. It can see faces and compare it with other faces. Those are patterns. What it doesn't know how to do is to extrapolate and to reason, and that's artificial intelligence, basically what we do up here. And that's what's needed for diagnostics, that's what's needed for determining the solution to a problem, and this is where it really gets interesting, and we're doing POCs around this area already. Ultimately then, what you want to do is shrink that whole MTTR region down to as close to zero as possible. So detect the problem, immediately figure out what, do the diagnostics automatically, figure out what is the root issue, or colloquially the root cause. Interpret, given the context of what's going on in the network, what could be the fix. Get approval for the fix, and implement the fix. Reduce MTTR. And then, of course, as regular insights and reports state that, you know what, all our problems, or most of our problems, have to do with this particular CMTS and this firmware that may be running on it, or this issue. So next time you do change management, put that at the top of the list, and that will then increase your MTBF. So those are the things that we're trying to do here with the applications and the analytics. Now, the nuts and bolts, when you look at all these different things, problems that you're trying to address, what they boil down to is answering these questions here. What's happening, and what is the bad thing that is actually likely to happen, what caused that bad thing in the first place, and how to fix it. These are common themes, so when we create these analytic systems, essentially all we're doing is trying to answer those kinds of questions, and then build applications based on those answers for the specific use cases at hand. And what we found is that you can't go after the mega use cases. You can't solve world hunger with one application. What you need to do is focus on specific smaller problems that have meaningful actions and outcomes to specific operations teams. And we call these micro apps. And they may be simple questions as to, okay, I have a set-top box. When there are errors on that set-top box, it produces, as an incident, a video quality problem code. Just that is a micro app. has meaning to someone who is focused on just that problem for their customers. And you create, in answering these questions, you create a microapp for that purpose. And that's then built on the data that's coming in through the lake, streaming off the set-top boxes and so forth in real time. Those same data can answer another question for another team. And so you get sort of a reduced TCO by leveraging the same data to solve different questions for different people within the organization itself. And so you need a platform that does this for you. So you can build these successive microapps one after the other as you need to address these problems down the road. And that's what we found is the best sort of architectural model for these solutions. Not siloed, verticalized applications. So let's look at some use cases that are on the proactive side of things. And there are lots of them. We talked about the care events, so you can imagine use cases that are about when a subscriber calls in, the care agent sees the top 3 issues that they're likely to call in about so they can reduce the average handling time and so forth. I'm going to focus on the ones that are about reducing truck roll because everyone appreciates reduction of truck roll. You can actually point and say, I saved that truck, so I saved $60. I can attribute it back to the analytics itself. So it's a nice, clean concept. So the prototypical example is as a subscriber, I'm just speaking now as a subscriber, I get frustrated when a truck comes out to my house and the problem is not in my house, but it's somewhere in the network and a line tech has to be sent out later on. And that just totally kills my NPS, my personal NPS back. And this is the prototypical example. Now, as an operator, you just wasted a truck. That was like $60, $70, $80. That happens, as you all know better than I, that happens many, many times per hour, if not certainly per day. So the prototypical example is, can we actually determine that a truck should not be sent to the home, but should be sent to somewhere in the network, maybe to the node. In other words, field technician out versus line technician out. And so we've built, Mohammed talked about models, we built solutions that are actually doing this, which is you're looking at data that's coming off of the CPE device itself, whether it be the set-top or the modem or what have you, coming off of that device. And in real time, you're able to say the problems you're seeing there are suggestive of requiring a line tech versus a field tech. That then goes and is made available to the operations folks as they create these tickets, to the care folks as they create these tickets, and they can make that immediate determination informed by that information. Oh, you know what, I was thinking about sending someone out to your home, but this thing is telling me I should send the line tech out. And you send the line tech out. And that, of course, saves. The other thing that it does is that suppose there is a problem that's occurring inside the network. Not everyone is going to call in, because first of all, they may not be witnessing the problem. Secondly, they're too busy to call in. Third, they're just not that type of person who's going to call in. So there are a lot of these what we call silent sufferers. They're your worst enemy, because what happens is that when those silent sufferers have to promote you, you know what they're going to do, negatively promote you, but you would never even know that they were suffering to have actually changed their minds to begin with. So by detecting that this is a network problem, you're also going to solve the problems of lots of other people who didn't call in and reduce the impact of those silent servers as well. So there's that collateral benefit apart from the actual cost savings itself. So here's an example of the typical sort of results what we see with that sort of solution. And what we have here is our ability to predict that a line tech should be sent out versus a field tech, and the predictions with different levels of accuracy. This is machine learning. It's not perfect. It's largely based on statistical phenomenon. Any one guess has some chances of being wrong. And what you see is the ability of the model to do its job. So let's say we wanted to get a handle on reducing by 45% the number of incorrect field trucks that are sent out. We can do that with 85% accuracy. That means that if we make a prediction that you should send out a line tech, there's an 85% chance it's going to be right. Okay. Similarly, if we wanted to reduce it, let's go to the other end, and reduce it about a third, resulting in a savings of a third of those false trucks that you're sending out. Then we can do that with an accuracy of 95%. So if we make a prediction, 95% of the time it's going to be right. So there's flexibility in which of these regions you want to work with within your business model in actually reducing a larger number of these things that are going out, but still allow for some incorrect or false positive predictions versus making sure every single one is right, but you're not going to be able to reduce as much. And this is the level of accuracy that these systems are able to generate. And you can compare that with your own current processes and workflows with human-led processes and workflows and their accuracies in doing this. What we find, Mohammed talked about some of the data and what we call features are extracted from them that are characteristic of the phenomenon that's going on. What we find is that these are the most important data elements or what come to us as KPIs. The fiber nodes to which the device is connected, the firmware version to which device is running, how many times it's rebooted. Some people reboot the devices every day, but other devices, because of issues, reboot multiple times during the day, so the number of times they're rebooted. These are obvious things. The code word error rate, another one. SNR, the upstream and downstream power, are also other factors. So these are the key factors that we find that you have to pull off of the data stream to inform the model so that it can make its prediction. So if you have these sorts of data lying around, speak to us. We can make use of it for this purpose. So that's one use case. And that use case was looking at CPE equipment. Now we're going to go a little bit further into the network, and we're going to look at edge network equipment, so CMTS, head-end, and whatever. And the same story applies there, technically that is, same analytics, you just shift it over into the network a little bit. The data sources are different, so you got to worry about how you get those data, and then the features are slightly different. These are all things that are in the weeds in terms of implementing the solution, but nevertheless you get there. The benefit in this case isn't the sending of the trucks to the CPE or to customer premises, excuse me, but is whether or not a truck should be sent to that edge network equipment, or you can actually fix that equipment remotely without sending a truck. So again, it's a truck roll or technician savings, and the question is, can I do a remote fix versus actually sending someone out? And that's how you save the trucks. And so when we do that kind of modeling, again, here is the kind of accuracy at which we were able to predict. For 31% of the time when you can just actually do a remote fix, we are getting accuracy or a precision, as we call it, of 77%. 77% of the time you're going to be right. And you can again model the savings, in fact, that instead of sending that one person out, roughly 30% of the time you're going to be able to save that person when they shouldn't be going out, and you're confident that you're going to get about a 77% chance of being right. These numbers add up to tens of millions of dollars per year in the customers that we work with. And if those numbers are meaningful to you, then I urge you to consider, whether it's from us or someone else, consider these sorts of solutions. You can go further in and talk to the data center. And similar sort of problems occur there. I won't repeat the details of the use case, but you can imagine the same thing translates over there. And there you're looking at syslog data, there you're looking at alarms, and you're doing the same sort of thing. What sort of incident is this going to lead to? But there, the business model isn't about sending trucks. You're not going to send a truck into a data center. The business model is about reducing the time of the technicians to actually fixing the device in the data center that they need to fix. So it's a human cost of time to resolve the problem itself. Similar analytics. But I'm going to leverage this slide to actually talk about some of the challenges that Mohammed spoke of earlier, but in this particular context. And I'm putting aside the business challenges, just the technical challenges. There are typically two types of technical challenges that we see, and they both have to do with the quality of the data. First, getting access to the data. Are we all familiar with that problem? We think it's in the lake, but is it really in the lake? Is the data that the machine needs actually in the lake, or is it the data that technicians are accustomed to using in the lake? That's the first question. And it turns out the machine doesn't necessarily need the same data that the humans need. And we run into problems there all the time. Secondly, even if the data is there, it's often very noisy. Lots of records are dropped by these devices as they're spewing out information. Their principal job is not to produce data for our analytics system, it's to actually deliver the data over the network to the subscriber. And so lots of data gets dropped in favor of their principal mission itself. So this, the issue of missing data is a big problem. The very nature of what we're trying to do here is to find things which don't happen often. If failures happen often, then I don't think we would be in this room. We all appreciate that. The failures happen infrequently. Analytics, and machine learning specifically, is about statistics, so it likes to see lots of examples of things. Well, we're trying to figure out things that don't happen often, minimal statistics. That presents a challenge to analytics, to the noisy data. Taking analytics that's used for marketing and trying to translate it over into this space does not work. Marketing, they focus on things that occur often. Here, we focus on things that don't occur often. Tremendous challenges as a result of that. So dealing with noisy data is a very big issue. The second thing happens on the flip side. We talked about training earlier, Mohammed, and the examples of what you're trying to predict need to be taught to the system so it can detect the patterns and connect the dots. The examples typically come from tickets. Who in this room has a perfect ticketing system? Who in this room will look at their ticket data and say, yes, the technicians who are entering information in that ticket data do a perfect job? Is anyone? See, 0 is an interesting number. Very interesting number. The analytics has to deal with that. There are all sorts of ambiguities. We all know that there are trainees that come in and there's a high turnover in the agents and so on. That manifests itself in the ticketing data. The time at which tickets are issued varies. There's no consistency. The machine has to connect the dots and figure out that this error over here is related to this ticket that was issued at such and such a time. When there's no consistency when those are issued, the machine has no clue as to what to do. So there are technical challenges associated with the ambiguity and the human activity itself and the workflows that the humans are actually doing. And that presents an enormous challenge. So this is not textbooks analytics. This is really real-world analytics where you have to face and deal with these inherent challenges. And so if you speak to a vendor about analytics, make sure they know how to deal with these and they aren't just applying, whatever open source classification algorithms that they may happen to find. So hopefully that's given you a sense as to some of the benefits of applying analytics, 4 to 5, 6, 7% savings in truck rolls, for example, equating to like tens of millions of dollars per year, 1% improvement in NPS from -6 industry-wide to maybe -5, significant improvement. And the kinds of data and challenges that one needs to deploy such systems. So if you have alarm data, if you have KPI telemetry data, if you have syslog data, or any of the above, even one of those, you can derive some of these benefits today. And we're here to help. Thank you.
Thank you, Roger. Okay, so we're at the Q&A session now. If you have any questions, please step to the center mic. Is that a question or is that a department? Okay, so I have a couple that I'll start off with. All right, question for Roger. So of the major problem groups identified out of your workflow, have any of the groups pointed to possibly additional training necessary for either the care agent or the field technician, or possibly even the customer, that they're, any of the human factors identifying? You talked in your slides a lot about equipment failure issues. Are there any human factor issues identified as a major group?
Absolutely. So we've been doing a project with a customer who was actually looking at trying to predict the sequence of events that the humans ought to be engaging in Because when these problems occur, the humans have to figure out what should they do next, look at their workflow, and then within the context of the workflow, what should they do next, what should they do next, and that takes time. So we're actually trying to reduce that workflow time to as minimal amount of time as possible by actually recommending a sequence of steps directly that they should be engaging in actually executing those fixed workflows. So that's one example, and of course that requires now that they take input from these machines. Okay. And there are a lot of factors associated with that. And to be absolutely blunt, there are a lot of ego factors associated with it as well. The second aspect of it has to do with fitting into the overall operational model, your operational model. And what we've found is that a big factor in the success rates of these don't have to do so much with the technology, but have to do with how are you going to operationalize this. We can predict that there'll be an impact on the video service because of these various factors. But if no one picks that up out of their inbox and does something with it, then that prediction is worthless. So figuring out how to operationalize these things is absolutely key in order to actually manifest the kinds of ROIs that are being professed here. And the customers we've spoken to, when they see the 4-7%, is because they're taking the initial steps and figuring out that operationalizing. They haven't figured it out completely, and so hopefully those numbers will increase, but even the small steps that they've taken are manifesting those numbers.
Thank you, Roger. I'd like to thank Roger and Mohammed this morning.